everyone. I think we have only a few people here. That's fine. I'm so glad to be here. I just arrived here like 3 hours ago from Columbus, Ohio. So um, I'm Jianli. Today I'm so glad to give the presentation introducing our work about the UAS navigation in the real world. This work is based on our previous work about the UAS navigation. The biggest difference between like the area platform and other platforms, such as the ground platform is that the aerial vehicle can fly freely like in the open space instead of like you are driving on a road. You have to follow the follow the rule and the road network. So the area environment allows the UAS to move freely and with infinite action space. Therefore, the navigation in the real open space is more complicated compared with the ground navigation problem. So in this work, we train an unmanned aerial system to do a long-range visual navigation in the real world. Our idea is inspired from dual process visual navigation system of human intrinsic, such as because the environmental understanding and the landmark recognition. Just imagine like when we are walking, following a guidance on the Google map to a target place, just near our house. Even though we lose the GPS, we have no ability to like localize our position on the map. But we can still find the way by recognizing the landmarkers around you, right? Because there is, this is this is a CBS like around my apartment. That's the tree standing behind my apartment. So in that way, I can say, okay, I can walk in this way or that way until I arrive at my house. So inspired from that idea, we do the same thing in our problem that we can recognize the landmark taken from the UAS and take actions such as turn left, turn right, go straight, go behind, based on what the UAS see until it goes to the destination. So ideally, our problem is divided into two phases. The first is the agent learns the navigation policy using the reinforcement learning in a specific environment. To achieve this, we design on interactive environment for training process. For example, during the training, we let the agent to learn to move forward while saying like the landmark 4. We ask the agent to move forward, or say when you say landmark 7, just move right. So once the agent learns the navigation policy, which means familiarize themselves with the environment, ask themselves to learn how to navigate themselves in the real environment. That's our purpose. So we let the UAS fly in a real world to recognize the landmarks using the image match method and take action according to the learned policy. The UAS nav environment is designed for training the agent in a policy learning phase. So This environment is in a 400 meters by 300 meters area in the residential block. And we select 100 points, very like uniformly distributed in this area, in a like 10 by 10 pattern. So, and the horizontal spacing is 40 meters, between two adjacent points, and vertically is 30 meters, and then the UAS flies in 60 meters in height. So this with this landmarks act as the ground control, at each point we just extract Google map image, Google satellite image as its landmark. So it's that's what the UAS see at this exact location. So at the 100 location, there are absolutely 100 landmarks for them, and the UAS needs to learn how to recognize those landmarks and navigate itself until the destination. That's our goal. So here, what we did is we implement the double critical Q learning model for the positive learning. Our approach is reinforcement learning. This is how we formulate this navigating task into a Markov decision process and the RL framework. In this framework, we have agent, environment, observation, action, and reward. The agent takes observations and does actions at the landmark position, which are move forward or backward or turning left or right based on what cases and interaction with the environment. The training program shows the fast convergence. Here. It's here. Oh, it's here. So the training process shows the fast convergence of our algorithm. The reward of this figure indicates the cumulative reward computed at each episode as the agent reaches the destination. As shown in this figure, the below figure, the agent learns policy within 200 episodes. So which means after training this agent to learn the environment, learn the navigation policy, after 200, you say, the reward convergence reaches the mid. Now the agent will know how to navigate itself to the destination. We also run the evaluation for 100 episodes in the real environment and demonstrate the agent being able to find the target in 6.5 steps in average. So during the real test, the agent needs to take actions while seeing the known objects based on what it has learned. This is a landmark recognition process. The UAS nav environment, we have the satellite image as a descriptor corresponding to each landmark. That's what I said. There is 100 landmarks uniformly distributed in a given space, and for each landmark there is a Google line and as a descriptor of that point. So in the environment, we have the satellite image as a descriptor, and while navigating in the real environment, the UAS take the real-time image, the real-time observation using its embedded camera, looking downward, and And in order to make decision on the actions at these ground control points, based on the learned policy, we need to enable the UAS to recognize the landmark during the navigation process. So we therefore use image matching approach to match the environmental landmark with the landmark is the Google satellite image there. And the other one is the real observation, simply say the image taken by the camera embedded on the UAS. So those are two images. Our goal is to match those two images so that we know, so that we can we can just say there is a landmark with the agent arrived on this a certain space. So we need to enable the UAS to recognize the landmark during the navigation process and to ensure the UAS exactly arrives at the matched landmark position. We also have very detailed methods such as the fine matrix to calculate the center distance between the landmark and the real observation. So we once it has the shortest center distance, we consider the UAS has arrived at that landmark position and it should take action correspondingly until it reaches the final destination. Oh yeah, sure. I just have two more slides. And by introducing the idea of landmark recognition using the image matching approach, it has robust performance regardless of illumination, variation, or seasonal changes. You see, the observation, winter and summer is kind of different from the satellite. So our method takes this advantage, and therefore shows the ability to resist environmental variation and is applicable in different seasons or most weather conditions. In the real world test, we use the UAS to fly in the residential area, which is the same as the environment, the training environment. The UAS is firstly set to a known starting point, and then use only embedded camera to get the observation during the whole process. Once it matches the landmark, the drone, the UAS will choose action to either to fly towards forward or backward or left or right based on the output policy of the reinforcement learning algorithm. Here is our final.
At last, I'd like to show the video of an example navigation process that illustrates how the UAS navigates to the destination.
Yeah, that's the other of our works. Yeah, they just pre-recorded. Okay, so here is a drone taken video showing how it navigates itself to the final destination, which is the last image. You see, this is a camera embedded onward. So the view is pretty similar to the satellite image. Here, there we go. Yeah, it reaches the final destination.
Okay, that's all about the presentation. Thank you.
Thank you, guys.